This will be the 25th lecture of EC 253C. In previous lecture we discussed in previous 3 lectures actually we have been discussing about timers, and in previous lecture we discussed an example that demonstrates how timers can be used to generate time delays. So we wrote a program to actually generate a square wave on one of the pins, and to generate the time delay between turning it on and off the square wave on pin 5, we had to insert delays, and that delay was created using timer 0. And then we calculated the delay amount. We know that the delay amount depends upon the crystal frequency and the prescaler used. We had not used any prescaler, so we calculated the delay amount. That actually also depends on the value we initially load in the counter register. So in our case, the total delay was 1.06 microseconds, and we also calculate what can be the maximum delay that we can actually generate using an 8-bit timer, for example timer 0, and that with no prescaler, that came to be 16 microseconds. This is the maximum delay that we can generate using no prescaler for an 8-bit timer, because 255 is the maximum value. Actually 0 is the minimum value that we can load, and 255 is the maximum value it can reach while counting. So 255 and 1 for the overflow, 256 into 0.625, that comes up to 16 microseconds. That's the maximum delay we can actually generate using timers with no prescalers. Then we also discussed what if we need more a time delay that is greater than 16 microseconds. What if we need 150 microsecond time delay or 160 microsecond time delay? What we use? Obviously we can switch to timer 1, or alternatively we can also use prescalers. So for example, if instead of loading I had loaded TCCR0B with 01, that actually started my timer in normal mode with no prescaler. This instruction here, these two instructions, I had loaded 01 in R20 and then copied R20 in TCR0B. This actually started my timer 0 in normal mode with no prescaler. What if I had put some other value in it? For example, if you might be remembering the table, I will be discussing that table also. For example, if I will be putting instead of 01, that is 00000001 in binary, if I be putting 00000100 in TCCR0B, in this case my timer will start timer 0 in normal mode, but with a prescaler equal to, and that prescaler in this particular configuration will be 256. So what will happen actually? My timer will not count at a speed that's equal to the crystal frequency, but at a speed that's lower than the crystal frequency by a factor of 256. That means the my crystal frequency is 16 megahertz. The frequency of my timer will be 16 divided by 256 megahertz, and time period of the timer will be the inverse of the frequency, that's 256 divided by 16 microseconds, because we have megahertz here. That comes up to a time period will be 16 microseconds. That means each tick will take 16 microseconds, and the maximum we will get when we load the counter register initially with 00, we will get 256 increments. 256 increments will therefore take 256 into 16 microseconds. That is 250, 512, 1024, 2048, 4096 microseconds. So the maximum time delay we can generate using timer 1 by using 256 prescaler is 4096 microseconds. Similarly, we can use other prescalers also. The highest prescaler we can use is 1024. We'll be discussing this in a short while. Today we'll be discussing one another thing. What if we have been given a time delay? For example, we need x milliseconds or x seconds or x microseconds, x seconds of delay. Time delay. We need x seconds of time delay. How do we calculate, or how do we calculate the value that needs to be loaded in timer counter register, that's TCC and TX and T in our case for timer 0, TCC and T0. So given that we need, there's a in our problem or in a particular programming scenario, we need x seconds or x milliseconds, microseconds of time delay. So how do we calculate what value we should load in that what value we should initially load in the timer counter register before starting our timer? How to calculate that value? And this we can calculate when we know, we have to assume we know the amount of time delay needed. We also know the crystal frequency, because that's also important. Unless otherwise stated in Atmega 321 microcontroller programming, crystal frequency should always be taken 16 megahertz. Or if there is if the question states some other crystal frequency, then we should take that one also. So how do we calculate the amount, the value or the number that needs to be loaded in timer counter register? What are the steps? The first step is we should actually calculate the timer clock period, or the period of time period of timer clock. How do we do that? We should know that f timer, the frequency of timer, is equal to frequency of the crystal for no prescaler. But if we use prescalers, and you should remember we discussed this thing in one of the previous classes, that we have 3 bits in timer control register B: CS02, CS01 and CS00. By loading different values in these 3 bits, we can actually configure the timer to be used in different modes with different prescalers, or also as a counter. If we load 000 here, that means the timer frequency, we are not feeding any frequency to a timer, that means our timer won't work. But if we are loading 001, that means our timer, in this case timer frequency f timer will be equal to f crystal. And for values 010, F timer, you should remember, F timer, the frequency of the timer should be equal to or will be equal to crystal frequency divided by 8. That means we are using a prescaler, and the prescaler value is equal to 8. That means our timer will run slower than crystal frequency. And how much slower? 8 times slower. Similarly, for the values 0, 1, 1, frequency of timer will be equal to frequency of crystal divided by 64. For 0, 1, 1, F timer will be equal to F crystal divided by 256. And for 101, sorry, for 001 it was F timer crystal. For 010 and for 011, frequency timer was equal to frequency time crystal divided by 64. So this is 011 here, the fourth case, and the fifth case therefore will be 100. And in this case, frequency of the timer will be equal to frequency of crystal divided by 256. And for the case 101, F timer will be equal to crystal frequency divided by 1024. This is the highest prescaler we can generate at Mega 328 microcontrollers. For other two configurations, for 110 and 111, the timer will be actually used as a counter to count the events happening outside the microcontroller. We have not discussed counters yet. So once we get, so the first step is to calculate the frequency of the timer. How do we calculate? Using these formulas. We should know what value we are going to load in the timer control register, timer control register B, and depending on that value we will get our timer frequency. Okay, once we have determined the timer frequency, we will get the time period, that is timer time period, T timer clock. So this is our first step, to know the T timer step, T time period of the timer clock. Okay, in the second step we will calculate an integer n that will be actually equal to the desired time period, T desired, how much time period we want to generate, divided by the time period of the timer we had calculated in the first step. In the third step, this number n will be subtracted from the highest number the timer counter register will get. In our case, in timer 0, it is 256. That means 256 minus n. And then this number will be converted into hex and loaded in TC and T0. So we have three basic steps. In the first step, we determine the timer frequency. That actually depends upon the crystal frequency and the prescaler we have used. In the second, and then we get the timer time period. In the second step, we divide the desired time delay that we want to generate divided by the timer time period we have calculated in step 1. We get a number n, integer number n. In fact, we usually round of this n. If we get a decimal fraction here, we round it to the nearest integer. And in the third step, we subtract the number calculated in step 2 from 256. The value we get is converted to hex and loaded into timer counter register to actually get this desired time period. Let me do an example. It's example 9.7 on your book. We have been told that the crystal frequency we are using is 16 megahertz. And we have to generate a square wave of 100% duty cycle. and frequency equal to 160 kilohertz on pin PB, for example PB3, port B pin 3. So 100% duty cycle simply means the square wave will be on and off for equal amounts of time. So frequency is 160 Hertz. What will be the time period? Time period simply will be 1 divided by 160 milliseconds, or I can calculate it. 1 divided by 160. Let me get the calculator. That is 0.00625 milliseconds, or we can say time period is equal to 6.25 milliseconds. Oh, sorry, microseconds. So the time period of this wave is 6.25 microseconds. That actually means the wave is on, or the square wave is high for half of this time period, that is 3.125 microseconds, and it's off for 3.125 microseconds. Fine. So the delay we want to generate is 3.125 microseconds. This is our T desired equal to 3.125 microseconds. Now we should decide on what prescaler to use. Can we generate 3 microseconds using no prescaler? Yes, of course, because we can generate a maximum of 16 microseconds using no prescaler. So we won't be using any prescaler. If we won't be using any prescaler, frequency of the timer will be equal to frequency of crystal. You should remember that the what prescaler to use will actually be determined by this T desired. What is a desired time delay we want to generate? If that is, for example, more than 16 megahertz, then we can't go with no prescaler. Then we have to use some prescaler. I'll be doing another example after this. I will show you how we actually determine which prescaler to use. So here, since we are not using any prescaler, because simply we can generate 3 microseconds using no prescaler. So now the frequency of the timer will be equal to the frequency of the crystal, and that's equal to 16 megahertz. And time period of the timer will be equal to 1 by 16 megahertz, that we had calculated in the last class. That was equal to when 16 megahertz, 1 divided by 16, 0.0625 microseconds. So the time period is 0.0625 microseconds. Fine. So the first step was to calculate the timer time period. We have done that. What was the second step? The first step, timer time, to calculate a number n, an integer n, that's actually equal to the desired time period divided by the time period of the clock. So what is our desired time period? 3.125 microseconds. So the number n will be equal to 3.125 microseconds. Micro in the numerator and micro in the denominator, that would cancel out. So I won't be writing micros divided by 0.0625. So my n will actually be equal to, let me calculate it, 3.125 divided by 0.0625, 0.0625, that comes up to exactly 50. 3.125 divided by 0.0625 equal to 50. So in this third step, what we have to do 256 minus this n minus this 50, that is 251. And now I have to calculate this 251 to hex, or I can simply load into the TCC and timer counter register. If I had to calculate, I can use a calculator to convert in hex, or simply I can say that hex will be 1 2 4. First I will convert in binary: 16, 32, 64, 128. So it will be 128, 1 here, 128. There are other methods also to convert into hex, simply by repeatedly dividing it with 16. We can also use that method. Simply do it like this: 128, 251 minus 128, 123. So I'll be writing 64 here also, then 64, 59, 32 also, 27, 16 also, 11, 8 also, 3, 2 and 1, 0. This will be our 251, and this in hex will be F, and this is 8, 9, 10, 11. 11 is B, FB. So this value will be loaded into TC and T0 register. So again, now we have to generate this square wave, and since the duty cycle is 50%, we will be on and off for equal amounts of time. So it will be, the program will be similar to this one, only the values that will be actually loaded to the registers of the timer will change. So in this program we will be actually loading, instead of loading we will be loading 0 0 into TCC R0, we will be loading 0 1 into TCC R0B, because we are again using normal mode with no prescaling. But here into TCC and T0, instead of loading 0 into 0 F0, we will be loading 0 into FB, because this time we want a time delay of 50 microseconds. First thing, and then I don't think there will be any other change. The program will remain as such, or I think I made a mistake here. I needed a time delay of 256 to 50 microseconds of not 50 microseconds, 3.125 microseconds. I got this number and 50. So 256 minus 50 is not 251, it is 206, sorry, 206. So 206, if I want to convert into hex, it will be equal to, this time I will use my calculator, 206 into hex, this is equal to CE. So this CE, not FB, will be loaded into TCC and TO register. So this CE will be loaded into the timer counter register, and timer will start counting from CE, CF, D0, D1, D2 up to FF, and then it will overflow. And when it will overflow, we'll have our required or desired time delay, that's equal to 3.125 microseconds. So I think this is very easy to actually know. So our registers, the program will be similar to the previous one. You can check on the book also. We all only should know the values that we have to load into our timer registers. In TCC and T0 we have to load CE, in TCCR0A again 0 0. In TCCR0B we have to load 0 1. Let me do another program in which we would be forced to use a prescaler. Example, let me take example 914 of your book, 9.14, or I will slightly modify it. So I have to generate a square wave of 250 hertz on, okay, maybe I will write this whole thing down. Generate a square wave of frequency equal to 250 hertz and 25% duty cycle on any of the pins, maybe PB3 again. Okay, so how do we do that? This time the square wave is equal to 250 hertz. That means f equal to 250 hertz. Time period will be equal to 1 divided by 250 hertz. That will approximately come to 1 divided by 250 seconds, or I can write 1000 divided by 240. Time period will be equal to 4 milliseconds. Okay, but also the duty cycle is 25%. That means it is on only for the 25% of these 4 milliseconds. Or we can use the formula. We know that the duty cycle is equal to T on duty cycle 25%. 25% equal to T on divided by T on plus T off, or T on plus T off is the total time period. We know the total time period here, into 100%. Cancelling 100 and 100, we will get 0.25 will be equal to T on divided by 4 milliseconds, or T on will be equal to 4 into 0.25 milliseconds, that is 1 millisecond. T on is 1 millisecond, for the rest of the 3 milliseconds is off, that means T off will be 3 milliseconds. So my wave will be something like this. It will be on for 1 millisecond, and then it will turn off for 3 milliseconds, and then it will repeat. So the total time period will be 4 milliseconds, so that the frequency is 250 hertz, but the on time and off time are not equal, because the duty cycle is not 50%, it's only 25%. That means wave is on only for the 25% of the time, that's 1 millisecond out of 4 milliseconds. So I have to actually generate this wave on PB3. I will do the same things, turn it on for some time, generate a time delay, and then turn it off and generate some other time delay. Simple, I will use the timers, but this time I have to first I will decide actually how to which prescaler to use, because that's important. You will be getting that in you will be knowing that in a couple of seconds, why that's important here, to know which prescaler to use. So I have to generate 2 time delays in this program. I have to generate 3 milliseconds, and also 1 millisecond. If and it's given that the crystal frequency is 16 megahertz. Crystal frequency is 16 megahertz, so the time period of my crystal with no prescaler will be 0.0625 microseconds. Okay, that's fine. That's when I use no prescaler. If this is the time period, what's the maximum time delay I will get? 256 into 0.0625. This is for no prescaler. This is the maximum time delay I will get. 256 into 0.0625. I think we have calculated that earlier. I will calculate that again. Just wait a second. 256 into 0.0625. That is 16 microseconds. 0.625 microseconds. This is a maximum time delay. 16 microseconds. But I need 3 milliseconds time delay. That means I can't use timer. That means I can't use timer 0 in with no prescaler. I have to use some prescaler. If I use a prescaler, what is my next option? To put instead of putting 001 in those 3 bits, I will put 010. That will give me a prescaler of 8. If I use prescaler 8 for my timers, what will be my timer frequency? F timer will be F crystal, that is 16 megahertz divided by 8, that means 2 megahertz. So the time delay will be, or the time period will be time period of the timer will be 0.5 microseconds. The maximum time delay that I will get will be 256 into 0.5 microseconds. That will be equal to 128 microseconds. Again, the desired time delay is greater than 128 microseconds. That means again I will not be able to generate 3 milliseconds using timer 0 with 8 prescaler. So I will go with my next option, that is using a prescaler of 64. If you check this table I had discussed earlier, where I discussed this 8 and then 64, then 256, then 1024 is the highest. So I will check whether I can use the 64 prescaler. If I use the 64 prescaler, the timer frequency will be 16 divided by 64. That will be equal to 16 divided by 64 equal to 0.25 megahertz or 250 kilohertz. And the time delay will be 1 divided by 0.25 divided by 0.25, that is equal to time period of the timers will be equal to 4 microseconds, and the maximum time delay I will get will be equal to 256 into this time 4 microseconds into 256, that's equal to 1024 microseconds or 1.024 milliseconds. Again, since I need 3 millisecond time delay, I won't be able to generate using 64 using the prescaler of 64. So I will go with my next option, that's using a prescaler of 256. If I use a prescaler of 256, the frequency will be equal to 16 divided by 256 and time megahertz, and time period will be actually equal to 256 divided by 16, inverse of it, microseconds, that's 16 microseconds time period. And the maximum time delay I will be getting will be equal to 256 into 16, that is 4096 microseconds or 4.096 milliseconds. That means I can actually use 256 prescaler to generate 3 millisecond time delay. That's equal to 3000 microseconds, because the maximum time delay I can generate is 4096 microseconds. And what is my second step? I have to divide n equal to, this time I have to get 2 different values, because when I turn on I have to give a different time delay, and then when I turn off I have to give a different time delay. When I turn on, the time delay is equal to only 1000 microseconds, because its on time is only 1 millisecond and off time is 3 milliseconds, that's 1000 and 3000 microseconds. So I have to get 2 different numbers. So n will be equal to, in case of when t on, for on period and off period, since I need 1000 microseconds here and 3000 microseconds here, so what will be my n here? N will be the desired time delay, that is 1000 microseconds divided by the time period of the time period of the timer. This time that's equal to the time period of the timer will actually be here equal to, since the frequency is divided by 256, it will be multiplied by 256. Time period will be, frequency is 256, 16 divided by 256. Time period will be 256 divided by 16, that is 16 microseconds. So my n will be equal to 1000 divided by 16, that's 62.5. let me round up that to 62 only, 62. And in case of 3000, n will be equal to 3000 divided by 16, that means 187.5. let me round off that to 187 only. So 187. So in this case, the value that needs to be loaded into the timer counter register is equal to 255 minus 62. 255 minus 62 equal to 193. And in this case, the value that needs to be loaded in the in this timer counter register will be equal to 255 minus 187. 255 minus 187 equal to, that is equal to 68. So this you can change into hex and load into TCC and T0 at the time of turning it on, and at the time of turning it off, TCC and T0 will get 68. But you should remember, since we have used a prescaler, 255 prescaler, that means TCCR0B will not be getting 0, 1, but a different number. And what is that different number? You can check from the table. That different number will be actually equal to, in binary, 0000 0100. That's in hex, it is equal to 012404. So you have to load TCCR0B with this number. This number will start the timer and start it with a prescaler of 256. You can do the rest of the program yourself. That's it for today's lecture. Thank you.